Sometimes when we're solving systems of equations, graphing is not going to be our best method. Graphing has several limitations. First, we have to graph it perfectly. If we mess up, we're not going to be able to see our intersection well. And secondly, sometimes our answers are going to be really large. Sometimes we're going to have x equals 100, y equals negative 40. Our answers are not always going to fit nicely on our graph. And occasionally we're going to have answers that are fractions or decimals. So those are hard to see that point of intersection on the graph. So we're going to learn an algebraic way to solve systems of equations. The first one we're going to learn is called substitution. Substitution is exactly what it sounds like. We're going to substitute or replace a variable in an equation with the value. So starting with example 170 here, we have two equations, x equals 5, y equals 2x minus 3. The nice thing about this one is we're actually given the value of x. So we know that the x value of our solution is positive 5. And now we just need to know the y value. So if we know the x value, if we have x equals 5, all we have to do is substitute that in for x right here and see what our y value is going to be. So we have y equals 2. We're replacing our x with the value of x minus 3. Okay, now we just simplify. We have y equals 2 times 5 is 10 minus 3, or y equals 7. So that tells me the solution to this system is 5, 7. Okay, example 171 is similar, except notice here we don't know the value. We don't know the numerical value of either variable. So we have two equations, 2x minus 3y equals 7. Our second one says y equals 3x minus 7. We don't know the numerical value of y, but we do know that y equals 3x minus 7. If we have one of our variables isolated, x equals something or y equals something, that's what we're going to use for substitution. We're going to substitute this in the other equation. Since it says y equals, we're going to replace it for our y. So let's see what this looks like now. We have 2x minus 3 times y, and notice here I'm going to replace my y with what we know y equals, 3x minus 7 equals 7. Okay, so all we did here, when we saw y, we substituted what we know that y equals. Okay, from here, this helps us because we have a one variable equation. We have an equation with only x's, and we know how to solve that. So let's distribute. We have 2x minus 9x plus 21 equals 7. Combine like terms, we get negative 7x plus 21 equals 7. Start isolating our x. We get negative 7x equals negative 14. Okay, last step to solve for x, we divide by negative 7, and we end up with x equals positive 2. Okay, but we don't stop here because we need to solve for our y as well. So we're going to use what we just found. We're going to plug 2 into one of our original equations. It mathematically does not matter which one we use, but since we're looking for y, I'm going to use the equation that says y equals. So we have y equals 3x minus 7. Well, we just found what our x value was. Our x is 2, so 3 times 2 minus 7. Now we just evaluate that right side. 3 times 2 is 6. 6 minus 7, negative 1. So our solution here is going to be 2, negative 1. And again, what that means graphically, if we were to graph these, that means that the point of intersection of these two lines is going to be 2, negative 1. We could always check our answer by substituting the values back into both original equations and making sure it's true. We could look at a graph, or we could trust our algebra on this one. Okay, a few more examples here. Looking at example 172. Notice here we have two equations where we do not have a variable isolated. We don't have a letter alone here. We don't have a letter alone here. We don't have an equation that says x equals or y equals. And that's what we're looking for when we're starting to substitute. But if you notice here, we do have this variable, this x that's kind of bolded there, that doesn't have anything in front of it. So this is pretty easy to get isolated. So if we want to get our x isolated, I'm going to add 5y to each side. And I'm just going to rewrite this equation as x equals 5y plus 6. Okay, now this looks like the one before. We can take what x equals, and in this time, we're going to plug it in for our x value since our equation says x equals. So when we do that, we have a 3. We're replacing our x with what x equals, 5y plus 6. Keep the rest of the equation the same, plus 2y equals 1. Again, we have a one variable equation left. We only have y, so we just solve from here. 15y plus 18 plus 2y equals 1. Combine our like terms, we get 17y plus 18 equals 1. Start isolating our y, and we get 17y equals negative 17. To solve for y, we divide both sides by 17, and we get y equals negative 1. We don't stop there. We've got to go and find our x. And again, mathematically, you could plug it into wherever you want. Since we're looking for x, I'm going to plug it into the equation that says x equals. We know x equals 5y plus 6, so I have 5 times negative 1 plus 6. This gives me x equals negative 5 plus 6, or x equals 1. So our solution is going to be the ordered pair x comma y, or 1 comma negative 1. Okay, looking at 173, notice we actually have a lot of options of variables that we could isolate. All of our variables, with the exception of this one, have a positive 1 in front of them and are pretty easy to get by themselves. I'm going to go ahead and isolate this x on the top equation. So I'm going to subtract y from both sides, and I end up with x equals 5 minus y. And that's the equation we're going to use to substitute. We're going to take 5 minus y, we're going to substitute it right here for this x. Okay, because there's nothing in front of this x, because there's no coefficient, there's really no need to put it inside parentheses. So I just replace the x with 5 minus y, and I keep the rest of the equation the same. Minus y equals negative 1. If I combine like terms, I get 5 minus 2y equals negative 1. Subtract 5 from both sides, and we get negative 2y equals negative 6. Using division, we get that y equals positive 3. Okay, if we plug that back in to solve for x, I'm going to plug it back in right here. Since we're looking for x, I'm going to use the equation that says x equals 5 minus 3, or x equals 2. So my ordered pair, we write our solution as an ordered pair, is 2, positive 3. Okay, let's look at a couple of special cases that we also saw when we were solving by graphing. Our first equation here, we don't have a variable by itself, but this y is pretty easy to isolate. So I'm going to rewrite this equation as y equals 3x minus 4. I'm going to take that 3x minus 4, substitute it for y. So we rewrite this equation as 2 times 3x minus 4 minus 6x equals negative 8. Okay, we solve from here. We get 6x minus 8 minus 6x equals negative 8. If we combine our x's, 6x minus 6x equals 0. So I don't have any variables left, and I'm just left with the equation negative 8 equals negative 8. There's no variables left to solve for, but we end up with a true statement. So if we have no more variables to solve for, but we have a true statement, we have infinite solutions. Remember what that means graphically. That means we have the same equation graphed twice. It's like we graphed our first equation, we graph our second one right on top of it. So they They intersect at every point. Every single point makes both equations true. So we have infinite solutions. On example 175, again, we don't have a variable by itself, but we can get this y by itself pretty easily. If we add 2x's to both sides, we get y equals 5 plus 2x. I'm going to take this expression and substitute it for y in this equation. So if we rewrite that top equation, we have 6x minus 3, we're replacing our y with 5 plus 2x, equals negative 9. If we solve from here, we distribute and we get 6x minus 15 minus 6x equals negative 9. 6x minus 6x gives me 0, and I'm left with negative 15 equals negative 9. Okay, there's nothing left to solve for. There's no variables left, but we are left with a not true statement. If we have no more variables, but we have a not true statement, we have no solution. That means that there's not an x and a y value that will make both equations true. It's like we have parallel lines. They're never going to intersect, so there is no solution. Okay, in our last one here, we're actually not going to solve this one all the way. Notice here that we don't have a variable that even doesn't have a coefficient. So we're going to have to make a decision here of which variable we want to isolate. There might be one that's easier than another. I'm going to just say, let's isolate this first x here. So if I'm trying to get that by itself, I'm going to add 6y. If we do that, we get 5x equals 6y minus 14. We can divide everything by 5, and we get x equals, 5. We get x equals 6/5 y minus 14/5. Okay, so if we were to continue to solve here, we would take this, which is kind of a nasty looking expression, and we plug it in right here for this x. It is definitely possible we can work with fractions all the way through, but it's going to be a little bit more complicated. So we kind of have two options. We could push along and finish using our fractions. We could see if there's an easier variable to isolate, maybe one from the second equation, or we could use a different algebraic method called elimination, and that's what we're going to look at next. This is an example of kind of a limitation of substitution. Sometimes you're going to end up with equations that are not super easy to work with, or you're going to be working with some fractions that are not super fun to work with.